Hello and welcome, class, to part 3 of chapter 9 in Burge and Overby's Chemistry Atoms First, where we are going to be talking about acids, bases, and neutralization reactions, all of which take place in aqueous solution. Now, we have talked about acids a little bit in the past, namely back in chapter 5, we defined what it means to be an acid, as well as we discussed the naming conventions for acids, and bases we end up naming kind of similarly to ionic compounds. So we've talked about how to name these things and how to address them already. What we're going to be spending our time here in chapter 9 on is discussing the more of like their chemical properties, as well as how these two things come together to interact chemically and undergo a neutralization reaction. All right, so we're going to be defining acids and bases all via the Bronsted-Lowry model description. So their definition of what it means to be an acid and what it means to be a base is really dependent on what solvent you're working with. And since we are working with aqueous solutions, according to the Bronsted-Lowry model, we have to define the acid and the base relative to the aqueous solution that they are existing in, that they are currently housed in. And the reason why is their definition of what it means to be an acid is not enough just to contain a hydrogen, which is kind of how we had introduced acids before, but also specifically these things, these molecules act as H+ donors in solution, meaning that the molecule is chemically interacting with the water, with your solvent, and that is what defines the property of acidity. So in the diagram, as well as the kind of chemical reaction, illustrated, written out down below, we can really see what this definition is getting at. HCl is defined as a Bronsted-Lowry strong acid, and the reason why is this species really readily donates H+ to solution. Well, it's not just enough for this HCl to break down into H+ and Cl-. Instead, this reaction is facilitated by the solvent itself, right? The solvent has to get involved. By definition and by observation, the following is a little bit more of an accurate representation of what occurs. So in the diagram or in the illustration down below, we can get a better visualization for how this HCl is interacting with water, why it breaks up in solution. Now we can see that the HCl is comprised of a partially positive hydrogen as well as a partially negative chlorine. And because of the polarity of this bond, we end up, concluding that HCl is a polar molecule. And as such, we know it's going to orient itself in such a way that the partially positives and negatives will attract each other with a different partially positive or a different polar molecule, such as water. And so in this diagram, the partially positive hydrogen is orienting itself to be near this partially negative oxygen. Well, because of the extreme charge difference within each of these molecules, they are not just polar, but both are very polar. The partially negative ends up pulling the partially positive hydrogen so strongly that it ends up just popping off of the chlorine. And so what we see on the right-hand side, this product side of the reaction, is that we are left with a chloride minus, since the hydrogen has left the chlorine and its extra electrons behind. We now have this negative ion in solution, as well as the hydrogen being chemically bound to the water, forming a brand new ion. And this is known as the H3O+ ion, also known as the hydronium ion. Now, in the bare bones kind of basic chemical reaction up above, this H+ that is written is actually meant to represent, or rather be a shorthand for the hydronium ion. So whether we are writing a dissociation reaction for the acid kind of existing in its form, and then on the product side breaking apart, as we can see existing as HCl here, breaking down into H+ and Cl-, all facilitated by water, the more accurate representation of this reaction explicitly shows water as a reactant and the hydronium ion as the product. The shorthand up above, this shorthand is an okay representation, just so long as we keep in the back of our minds that H+ physically, as it would exist inside of a beaker or a flask, anything in aqueous solution, is actually going to exist as this hydronium ion because it's much more stable for the H plus to exist this way, to be stabilized by the solvent, which is readily available and abundant around it. All right, but this is what it means to be an acid according to the Bronsted-Lowry model. Any acid or any molecule that we can categorize as an acid because it has some spare hydrogen, which is very partially positive, kind of sitting around in the molecular structure somewhere, it will interact with our solvent. And again, since we are working with aqueous solutions, our solvent is going to be water. So the same form of this reaction will be seen anytime we are observing an acid in solution. All right, so in continuing with the Bronsted-Lowry model, before discussing bases, we're going to also break down two additional kind of subsets or subcategories for acids. The first is the polyprotic acid, and the second is the amphiprotic acid. Now, the reaction that is illustrated down below, again in its shorthand, where H2O would be present over the reaction arrow here, we're seeing a dissociation reaction. Again, is a shorthand. We can keep in the back of our minds that this H plus is actually supposed to represent H3O plus. Perfectly fine as long as we can keep that in the back of our heads. This reaction is a great demonstration or illustration of not only polyprotic acids, but also amphiprotic acids. So polyprotic, if we break down this term, it literally means many protons. Right, poly for many, protic for protons, many protons. Well, if we ask ourselves what in this reaction is a proton, I mean, we're working with atoms here, right? We're not working with like subatomic particles. But if you can remember to what the construction for hydrogen is, hydrogen, the simplest atom on the periodic table, consists of one proton and one electron. Well, in order for hydrogen to exist as H+, we have to lose an electron for that to be true. H+ is literally just a proton. So a polyprotic acid is an acid that is capable of donating multiple H+, or multiple protons, to solution. And so H2SO4, we can see because there are two hydrogens inside of this chemical formula, it has the potential to donate two different H+ to solution. Now we can see in the way that this reaction is explicitly written, we have only lost one of our protons, only one of our H+ has dissociated away, but the other product, this HSO4-, we can see still has a hydrogen attached to it. It could in fact dissociate and give us a second H+ in solution in aqueous form. And all that would be left behind is our sulfate anion in aqueous phase. So H2SO4, we would say, is a polyprotic acid because there are multiple hydrogens that could be lost. So the definition of amphiprotic can also be thought of as like ambiprotic or like ambidextrousness, meaning that this is an acid that can also act as a base, can also act as a base. All right, so the definition of a base we can see down below. We're not going to focus on the two examples here quite yet, but let's read what this definition says so we can get an idea for what amphiprotic acids are. The definition of a Bronsted-Lowry base is something that accepts an H+ in aqueous solution. So an acid donates H+, a base will accept H+. The HSO4- in our previous reaction has a negative charge present. And as we know, negatives attract positives. HSO4 is an excellent example of an amphiprotic acid, because if it acts as an acid, what we're going to see are the products that are already written. We're going to see an extra H+ be donated to solution, and we'll be left with the SO4 2-. However, HSO4 with this minus charge, again, has the ability to attract an H+. And so if HSO4- were to attract an H+, what we actually end up with is a reaction that goes in the reverse direction and will regenerate some of this H2SO4. This amphiprotic acid has a little bit of an ambidextrousness. It can act both as an acid and as a base, all depending on the reaction conditions. If there is an abundance of H+, there's no reason to think why it wouldn't be able to hypothetically go back and reform some of this H2SO4. Is it going to be more than likely, or will it more than likely behave as an acid? Probably. Could it act as a base though? Technically, yes. So this is this HSO4- will be an example again of something that is an amphiprotic acid, something that can act both as an acid and a base. All right, so let's talk about our Bronsted-Lowry bases then in a little bit more detail. These are species that, again, will accept H+ in solution, either because there is a distinct negative charge present, such as can be seen on this OH-. OH with a minus charge specifically has a minus charge on this oxygen, which we would be able to determine based off of its formal charge. The formal charge on the oxygen in OH- is a -1, so this is where our negative charge is going to be present. As this comes into contact with a hydrogen in water or on another acid, maybe hypothetically that could be present, it is going to scoop away anything with a partially positive charge. Any one of these hydrogens, this negative charge is going to come and grab it. And what we're going to end up with is then this base having accepted the hydrogen, and the other species which will have lost its hydrogen. So in this hypothetical that I've drawn, our products end up looking the exact same as the reactants just because of how I drew the base interacting with our solvent here, which the solvent in aqueous case is water. So don't focus too much on the details in this case, but rather the gist of what it means to be a base. Here we have a species with a negative charge that is attracting this partially positive, and then the products will be the result of the hydrogen jumping ship and whatever is left over from the solvent, or if there is an acid that it's coming into contact with, whatever is left over there. Another great example of a Bronsted-Lowry base, and in fact was kind of like the kickstart for the Bronsted-Lowry model, like why it was so widely accepted off the cuff, is because it was able to explain the basic behavior of molecules like NH3. NH3 is also a very polar molecule. It does not have its own distinct ionic charge, but the nitrogen in this molecule is very partially negative. And so because it's partially negative, it's going to behave in just the same way as the negative on this OH did. Whatever solvent is present, or if there is an acid present nearby with a partially positive hydrogen, this partially negative nitrogen is gonna, in this much the same way, come out, scoop up that H+, and on our product side, we are then going to end up with the NH4+ ion, where the plus charge is specifically on the nitrogen, and we will be, again, left behind with this OH- anion, which is the result of the solvent, water, having lost one of its hydrogens. And so this is how we can think of a Bronsted-Lowry base. It will also be interacting with the solvent, pulling away an H+, or as we will be seeing, if we mix acids and bases, the acid is going to give up an H+ pretty readily, the base is going to take that H+ pretty readily, and then we're going to be able to predict pretty straightforwardly what our products are going to end up being as a result. All right, so before getting into neutralization reactions, let's focus a little bit more on the types of acids and bases, specifically the strong acids and strong bases, since these will be what we are focusing on at least in the fall semester. Strong acids and strong bases are known as strong electrolytes, meaning that they dissociate into ions completely, I'm going to say completely, when dissolved in water, when they are present in the solvent. So each one of these strong acids will behave like HCl did in the example a couple of slides ago. The H will be donated to our solvent pretty readily, and each one of these acids will completely dissociate and create a bunch of hydronium as a result. Each of these strong bases similarly will completely dissolve in solution, And it's not necessarily that the molecule as present or the compound as present is going to behave as a base, but rather the lithium hydroxide, for example, will break down into lithium plus, aqueous, and OH minus aqueous. And it's all of this OH minus that's present that's going to specifically act as a base. Because there's that negative charge there, it will readily absorb or pick up any H plus that is present, whether it be from the solvent or from any one of these acids when they get partnered together. All right, well, since we've introduced strong electrolytes, let's also talk about weak electrolytes. So a strong electrolyte was defined by those strong acids and bases. That's something that can completely dissociate when in the presence of the solvent, in this case, water. A weak electrolyte is only going to weakly dissociate or partially dissociate into ions when dissolved in water. And so as an example of a weak electrolyte, just to kind of dip our toes into weak electrolytes before we save most of the discussion for the spring, save mostly for spring. Let's just acknowledge what it is, what it looks like before we kind of, set it off onto the sidelines for now. Put it on the back burner, as they say. What is the chemical equation representing hydrofluoric acid partially dissociating in water? Right, again, a partial dissociation. Well, since hydrofluoric acid was not on the list of strong acids, we can conclude that it is going to be a weak acid. And this is going to be true of any acid or base we come into contact with. In order to determine whether or not an acid or a base is a strong acid or base versus a weak acid or base, all we need to do is look at this table. I'm going to clean it up a little bit. If it is on this table, it will be strong. This list is an exhaustive list. These are the, 7 strong acids and the 8 strong bases. These are it. So if you come into contact with an acid that is not on the strong acid list, or if you come across a base that is not on the strong base list, they will be weak acids and bases, period. And so since hydrofluoric acid was not on the list, we can conclude that it is a weak acid. And so what it means for a weak acid to come into contact with water, in aqueous form, coming into contact with water, which is the solvent, so since it's so readily abundant, we're going to define it as a liquid. In a strong electrolyte, we're going to have a complete chemical reaction, right? A total dissociation. Partial dissociations we notate by listing this forward and reverse arrow. What this means is that not all of the HF will undergo the reaction that we are about to see. Not all of it will break down into the products, and in fact, when the products are present, they will also turn back into reactants. So we have this dynamic, fluctuating reaction. It's never complete, it's always reacting, it's always going. The reactants are creating products, and the products are then in turn going backwards and recreating reactant. And so the products of this type of dissociation reaction, as we saw with the illustration before, to be an acid means that you're going to donate your H plus to something else. This means that the counter ion that's left, in this case fluoride, will exist on its own, and the other product will be that hydronium ion in aqueous phase. So the hydronium ion, as well as this fluoride minus, are not super stable products existing together, like cohabitously. So the fluorine is actually going to take one of these H pluses back and then revert into the reactant state. So this is what it means to be a weak electrolyte. And so this is why we save this discussion further for the spring. It's because this dynamic shifting causes, let's say, stoichiometry calculations or like observable, predictable measurements like pH, etc., to kind of shift away from what we would expect it to be, because the question is, how dynamic is this reversible reaction? So in order to answer that question, we need to wait until the spring, wait until we have a couple of additional, let's say, topics under our belts to really be able to understand what this dynamic reaction truly means. All right, so for now, again, we are going to be focusing on the strong acids and strong bases, those things that completely dissociate and will totally and fully react. How we measure the strength of an acid is through the pH scale. And the same goes for a base. Like the strength of an acid or a base in solution is measured using the pH scale. Now, the pH scale was developed specifically because it was determined that the strength of an acid scales logarithmically in solution. So, as such, the definition for pH is equal to the negative log of the concentration of H+. So that's what this square notation means. Anytime you see these square brackets, what it means is literally concentration of whatever is inside. So square brackets of X would mean concentration of X. In this case, with the pH equation, pH is equal to the natural log of, pH is equal to the negative log, of the concentration of H+. So we can see an example for calculating pH down below. What is the pH of a 0.0013 molar HCl solution? Now the place to start is to first and foremost recognize that HCl is not equal to H+, right? These two things are different. And so we're going to have to start by writing out a balanced chemical equation. Now HCl in solution, aqueous, is going to interact with H2O and will give us H3O+ in solution as well as Cl- in solution. Now, as we said already, this H3O+ concentration is synonymous with H+. These two things are used interchangeably. Now, over the course of this chemical reaction, we can see that everything is balanced and reacts in a 1-to-1. So if the concentration of HCl is 0.0013 molar, 0.0013 molar, surely this must mean, since everything exists in a 1-to-1, according to this balanced chemical reaction, there is 1 mole of our product, H3O+, for every 1 mole of HCl, and this is going to obviously then determine or mean that we are working with 0.0013 molar H+. All right, so this may have seemed like a formality to start with, but I do want to point out that not every acid dissociation does generate a 1-to-1 H+ to acid ratio. Sometimes you're going to be working with a 1-to-2 or even a 1-to-3. So it's really important when trying to set up and find a pH to first determine how much H+ is actually being generated according to your balanced chemical equation. If you are working with polyprotic acids, such as H2SO4 or H3PO4, you will have to pay attention to exactly how many hydrogens are being donated. All right, so now that we have our H+ concentration present, we can determine our pH, which is equal to the negative log of this concentration, the 0.0013 molar, that's a capital M, and the pH ends up being or equaling 2.89. Now, pH is a unitless number. It is, again, just kind of a point on this logarithmic scale where the closer to 1 you are, the more acidic your solution. So we can see here on the lower right, we have this pH scale that is illustrated where acids are presented here on the left. In fact, I'm gonna grab an eraser quick and just clean this up. Give me a second. All right, there. Now I've cleaned up the diagram a little bit. So we can see on the left-hand side, we have this label for acid. On the right-hand side, we have this label for alkali. Alkali in the more like olden definitions, the olden time definitions, is what we would refer to today as a base. The two are synonymous and interchangeable. All right, so to be pH neutral means that you are working with something that is not an acid or a base, and true pH neutral exists at a pH of 7. This is actually the pH of pure water, just water on its own, is going to have a pH of 7. So if you're working with just the solvent, in other words, and nothing is present inside of it, not even other ions, you will be working with a solution that truly has a pH of 7. Now everything to the left-hand side with low pHs are going to be acidic things, all the way down to a pH of 1 corresponding to the pH of battery acid. We can see pH of 2 is gastric acid, meaning stomach acid has a pH somewhere between 1 and 2. Hydrochloric acid, this is going to have a pH of around like 2 to 3. And we can see then ranging up. Sodas after this, acid rain, black coffee, urine/saliva. Now remember that this is a logarithmic scale, meaning that each jump on the scale does not, like what it represents is a change in the magnitude by a factor of 10. So in other words, going from like a pH of 6 to 5 means that you're looking at something that has 10 times the acidity. And so going from 5 to 4 means that you're also looking at something that has 10 times the acidity. So if we want to compare, let's say urine/saliva with a pH of around 6, let's just say saliva specifically. Soda, so like Coca-Cola, Pepsi, Dr. Pepper, whatever, which we can see on average has a pH of 4, is 100 times more acidic than your naturally occurring saliva. So that's what each of these tick marks represents. We're just adding another 0 to how much larger the magnitude is. Now, if we're going in the other direction, the basic side, we can see that seawater is like 10 times more basic than just pure water. Then there's baking soda, milk of magnesia, ammonia, soapy water, which truly soapy or detergenty water has a pretty like basic pH. And then we can see bleach is after that. And then last but not least, we have drain cleaner, which is like a combination of bleach and some other like cleaning agents, which make it even more basic. All right, so once we bring acids and bases together, this is how we then undergo neutralization reactions. So what we've been looking at so far is just how an acid or a base separately interact with their solvent and how we can kind of classify them based off of pH. A neutralization reaction is the type of reaction that occurs between an acid and a base. So as you bring an acid, which is an H+ donor, into contact with a base, which is an H+ acceptor, we're going to see a hydrogen or an H+ jump from the acid to the base. And on the product side, as a result, what we end up seeing mostly is water and some type of ionic salt. So for example, let's say we want to write out the neutralization reaction between hydrobromic acid and calcium hydroxide. Well, we first need to figure out what our reactants are. In this case, we're working with HBr, our hydrobromic acid, and calcium hydroxide is CaOH2. Now, each of these things, the HBr and the calcium hydroxide, are going to be dissociating in solution on their own before coming into contact with each other. That is true. However, it's a little bit easier to go a step backwards and write out HBr and calcium hydroxide before they dissociate in water to see in a more straightforward way how these two things are going to interact with each other. So it may not be as physically accurate, but it is easier for us, and as it turns out, the end result ends up being the same anyway. So we're going to start with the still combined HBr in aqueous conditions. We're mixing it together with calcium hydroxide, which is also in aqueous conditions. Again, acids and bases, as we are observing them, have to be present in some type of solvent in order for them to even be defined as acids and bases, according to the Bronsted-Lowry picture. So we have HBr, aqueous, as well as calcium hydroxide, aqueous, and these two things are going to come together and react. Now, the easiest way to write up this type of reaction is to treat it as a double displacement reaction, which I kind of skipped over in the definition up above, but it is a really nice straightforward way to go about this. So what we're going to do is swap the hydrogen, since again, this is an acid, it's the hydrogen that's going to be donated into solution, or in this case, donated to the base. This hydrogen is going to be swapped for the other species cation, right? Since hydrogen has a plus charge, we're going to swap it out on the other molecule for whatever has a positive charge there, which is going to be calcium. So as calcium moves to the bromine, we are going to, as one of our products, then end up with calcium bromide. And we also must make sure that we have charge balance in our species. Again, super important that we keep charge balance. Calcium, we know naturally has a 2+ charge. Bromine naturally has a 1- charge, meaning that if we want to make sure that our ionic compound is actually charge neutral, we're going to need 2 of our bromines to donate 2 negative charges, and that will then in turn balance out with our calcium and its 2+ charge. So we'll just get rid of these charges here. Calcium bromide will have 2 bromines for every 1 calcium. In order to determine whether or not this thing is aqueous or if it is a solid or a precipitate, we're gonna have to go back and check out our solubility list. So yes, we always will have to take into account solubility for our products. It's not always assumed that the species that is produced here is going to be aqueous. In other words, not each of these reaction types that we're talking about is mutually exclusive. Sometimes we have a precipitation reaction and a neutralization reaction at the same time. So in order to determine this thing's solubility, we can go back to our previous rules. As it turns out, bromine is one of those mostly soluble species, and as it turns out also, calcium is not on the list of exceptions for it, so this means that calcium bromide is going to be aqueous. It will be totally soluble in solution. The other product that is formed will be the result of combining H+ and OH- together, since OH- is what is present here on the anion side in calcium hydroxide. Now we can see that the 2 things are charge balanced already. We don't need any extra H+ or any extra OH-. This is going to exist in a 1-to-1. And funnily enough, HOH is another way of writing H2O. So as we bring together HBr and calcium hydroxide, one of our products, the first one that we wrote here, is a form of an ionic salt, right? We have calcium, which is a metal, bromine, which is a non-metal, and the other product is water, H2O. And this is going to exist in liquid form since, again, this is the solvent. It will be the most abundant species in solution. It's what's housing everything else. So as you mix HBr and calcium hydroxide together, you're actually going to generate some additional solvent for all of the other ions to still exist in solution in. Now, something else that is worthwhile to pay attention to over the course of a chemical reaction, a neutralization reaction, is what is known as the equivalence point. And the reason why this is useful to pay attention to is the 2 things that you're bringing together, your acid and a base, are not individually pH neutral, right? Your acid, as we saw in the previous diagram, has a pH that is less than 7, and your base has a pH that is greater than 7. So what happens when you take an acid with a pH of less than 7 and combine it with a base that has a pH greater than 7? Well, as it turns out, assuming you have completely reacted your acid and your base together, all that should remain is product. And according to our product side, if we observe this, sodium chloride is not an acid, nor is it a base, right? There's no H+ to be donated, and there's also no way that this thing could accept an H+ in a stable way. So this sodium chloride is actually pH neutral when it's in solution. Its pH is equal to 7. And the same thing can be said for our water. Water also, in its neutral form, is going to have a pH that is equal to 7. So what the equivalence point, what this definition means that I just totally skipped over reading, is that the equivalence point is defined as the point during the neutralization reaction when your acid and your base have totally neutralized each other. They have completely reacted. They are in perfect stoichiometric ratio, right? So the amounts of reactant being mixed are in perfect stoichiometric ratio. In other words, if you mix a 1-to-1 of hydrochloric acid and sodium chloride, you're going to go from two independent solutions that were not pH neutral and then generate something that is pH neutral at the equivalence point, at the point where you have an equivalent amount of your HCl and your sodium hydroxide. So observing the pH is especially useful when you're trying to mix HCl and NaOH or any type of acid and base together in perfect stoichiometric ratio without any type of excess reactant, right? Because the bummer of excess reactant, particularly if you're working on the industrial scale, is that it is wasted product. Right? Because of the limiting reactant, you'll never be able to turn this excess reactant into product. It's just a waste at this point. It's extra stuff. It's a bummer you can't react it. You're still missing reactant. You can't turn it into product. Well, if you have the means, such as observing pH in a really easy way using pH probes, which is they're readily abundant and very cheap nowadays, it's very easy to tell when your neutralization reaction is finished. It's very easy to tell if you have any type of excess reactant still by observing pH. Like if you're undergoing a neutralization reaction and you're monitoring pH from the start, let's say your pH is less than 7, and so you're trying to add base to bring that pH up. Well, you're going to know when you're done adding base, because when you reach the equivalence point, once this reaction is done, the pH is going to be a neutral 7. You don't need to add any more base. You have added the perfect amount of reactant to reactant. All reactants have turned into products, and you have no wasted product. You have no wasted potential. So the equivalence point, again, is going to be a really useful definition for us. It is the point during your neutralization reaction when everything is neutralized, and you can observe this pretty straightforwardly because when observing at least the mixtures of strong acids and strong bases, your pHs will be 7 at the equivalence point. All right, so our conversation of equivalence points has now brought us to our quantitative component of today's lecture, which is all about the chemically or analytical technique known as the titration. So just like how when we were observing the solubility and precipitation reactions, we then turned our attention to gravimetric analysis as a means to use stoichiometry to figure something quantitatively about the reaction that we were undergoing. Titrations are going to be that same type of conversation to us. So like, in other words, precipitate reaction to gravimetric analysis is neutralization reaction to titration. This is where we're going to start putting numbers to things, more so than just pH measurements. All right, so the usefulness of the titration is in determining unknown concentrations of acids or bases. So let's say hypothetically you're working with a solution that you know is an HCl solution, but your pH meter is broken, you don't have any litmus paper, you have no idea how to determine accurately what the concentration of this solution is. Well, you can use a titration in order, or undergo a titration in order to figure out what this unknown concentration is. How we approach a titration reaction is that we are going to perform some type of neutralization reaction, so we're going to need a known counter species, so in this case a base. Since our question mark is an acid, we're going to need a known base to kind of bounce off of that. And we're going to perform a reaction between these two things until your equivalence point is reached. In other words, you're going to perform this until the product is pH neutral, and once the product is pH neutral, then we can say the reaction is done. We can compare how much of the base we added, which because we're at the equivalence point, then the base and the acid have to be equal, right? So the amount of base and the amount of acid that we add if we are at the equivalence point has to be in stoichiometric ratio. Again, in other words, there's no limiting reactant, there's no excess reactant, they are present in perfect stoichiometric ratio. All right, so the device that we use to perform a titration reaction or a titration method analysis, we can see here on the right, this is known as a burette. The big advantage of a burette is that it is a large graduated pipette. And at least at the undergraduate level, burettes tend to be anywhere from 20 to 50 milliliters in volume. So this burette here looks, just by judging off of the tick marks, like it's probably around a 25 milliliter burette. And again, the great usefulness here is that it's a really nice way to measure volume of known species added. If you fill this burette up to the top, underneath the burette, this would be like hooked up to some type of like ring stand. Underneath the burette is where you would place your question mark, whatever this question mark concentration would be. And so as you turn this little spigot handle right here, the contents of this burette are going to flow out of the burette and into the flask that's sitting underneath it. And so you're going to monitor this flask or solution that is sitting underneath until it becomes pH neutral, pH 7. Now, again, your conductivity meter may be broken, but we have other ways to monitor pH, such as chemical indicators, special species that turn color once a certain pH is reached. So we can add something like phenolphthalein or bromthiamyl blue, which will then turn color once pH of 7 is reached. And so we're going to watch for the color change. Once the color down below has changed, we're going to, again, turn our spigot, cut off the flow, and observe how much of this hypothetical base, this known base, has been added. Once we know the volume in milliliters of this base that has been added, in conjunction with knowing its concentration, again, this is going to be a known base with a very particular concentration, we then know how many moles of base were added. We can figure out how many moles of acid must have been present in the flask underneath, again, down here, wherever the chemical reaction is occurring. And if we know how many moles of base were added, again, we know how many moles of acid must have been present down there. And so from that, we can figure out what the unknown concentration was. So again, let's plug in some numbers. Let's see how this type of titration calculation actually shakes out. You know, instead of in the hypothetical, me trying to abstractly explain how a burette works, let's just like plug in some numbers and see how the calculations work instead. So let's say we are taking a 25 milliliter sample of HI, or hydroiodic acid, and it is titrated against a 0.145 molar solution of potassium hydroxide. So here we can see that we are given a concentration, so we have a known basic concentration. I just want to like put a red flag in the sand there before we keep reading. We'll come back to why this is important in a second. A volume of 20.2 milliliters of potassium hydroxide is required to neutralize the HI. So at this point, we are at the equivalence point. Once we are at the equivalence point, again, we have neutralized all of our acid. These two things are synonymous. So if instead the wording of the problem said a volume of 20.2 milliliters of KOH was required to reach the equivalence point, that would mean the same thing as neutralizing the HI. And I'm just saying that for clarity in the future, in case you see the wording of the problems be swapped around a little bit. These two things mean the exact same thing. So our question then is, what was the concentration of HI in and the pH of the original solution? So let's find the concentration of HI, let's find the pH of this original solution. All right, so let's return to the very top of this problem. Let's just gather the information that we know. I am also going to gather the information specifically in the form of a diagram of the titration that would occur as it occurs. And the way that we always perform titrations is that the unknown is in the flask down below, the known is in the burette up on top. And so the 25 milliliter sample of HI we now know pertains to the unknown, since that's exactly what concentration and pH we're looking for. So I'm going to say 25 milliliters of the HI is going to be present down below. HI is what is inside of this flask. The known is going to be the KOH. The base is what is known. Known is base, unknown is acid. And we are told specifically that this base has a concentration of 0.145 molar, as well as a total volume of 20.2 milliliters was added down into the acid in order to neutralize it. What this volume means is that, regardless of however much total volume was present in this burette at the start, over the course of the chemical reaction where we turn this spigot on and KOH is flowing into this HI solution, a total of 20.2 milliliters was used. So that's going to be the volume difference that would be present inside of this burette over the course of the reaction. So we don't ever look at how much is left over inside of the burette, we're looking at how much was used. All right, so in order to figure out what the concentration of the HI as well as the pH of the original solution was, let's start by observing the balanced chemical reaction between the base and the acid as this reaction is undergone. Right, just like with our previous examples, going again all the way back to chapter 8, we need to have a chemical reaction present on paper in order to figure out how the rest of this information is going to be useful to us. So we're taking KOH, this is our base, we are mixing it with HI, this is our acid. And in mixing these two things together, we are going to assume some type of double displacement reaction. So the H is going to be lost into solution and will be swapped out for the other species cation. This is going to give us H2O as our first product and Ki, aqueous, as our second product. Now we can see here that everything is already balanced. There's no need for any other stoichiometric coefficients. This is actually going to make our lives a little bit easier because what this tells us is that the KOH and the HI have to interact in a 1-to-1 ratio. So if we can figure out how many moles of KOH were used during this reaction, it should be equal to the same number of moles of HI that were present initially. All right, so we can use the volume and the concentration information for the known base that we already gathered from the wording of the problem to figure out how many moles there should be, or how many moles were used of this KOH. So the, at least in my opinion, easiest way to go about calculating the total number of moles is to start with our volume, 20.2 milliliters. And the reason why I'm starting with this is because concentrations, which are equal to moles per liter in terms of units, can be used as a conversion factor. So if you're actually a little bit more comfortable setting this up as a moles per liter is equal to concentration equation, that's totally fine. I am just more comfortable with conversion factors because, to me at least, it's fewer steps, which means fewer places where my calculations can go wrong. All right, so I'm going to start with my 20.2 milliliters, and my first goal is to get this milliliters into liter. And the reason why is we can see in the unit conversion up above, capital M for molarity is equal to moles per liter. So I want to make sure to get this volume into liters. Well, there are 1,000 milliliters per every 1 liter. And then we can use concentration right away. Again, I'm just going to treat it as a conversion factor. There are 0.145 moles of this KOH per every 1 liter. And so I've gone from volume into moles in one calculation without needing to worry about my units any more than treating them as conversion factors. Got out of the unit of the milliliter and into the liter, got out of the unit of the liter and into the mole. Each of these, again, values pertains to KOH, so the total number of moles of KOH present is equal to 2.93 times 10 to the negative 3 moles. All right, and because according to our balanced chemical reaction, the KOH and the HI reacted again in a 1-to-1, the total number of moles presented here for KOH is also going to be equal to that same number of moles for HI that must have been present down here in the flask before the reaction started. In other words, 2.93 times 10 to the negative 3 moles of KOH can be converted into moles of HI because these two things react in a 1-to-1. 1 mole of HI per every 1 mole of KOH. Right, so I'm just trying to explain it verbally, show it in terms of ratios, as well as in terms of explicit stoichiometry, just to cover all bases here. If 2.93 times 10 to the negative 3 moles of KOH was used, this must mean that there was 2.93 times 10 to the negative 3 moles of HI in the flask to start with. All right, so now we know how many moles of HI were present. This doesn't answer the questions that we were asked initially, but this piece of information can be used then to find it directly. All right, so I'm going to erase a little bit of stuff just to give myself some more space to work. Give me a moment. All right, there, I've got a little bit of a window of space now that I can work. And in order to answer the questions, or at least in order to calculate the things that we were asked to calculate, which was the concentration of HI, as well as the pH of the HI solution, we now have the means to do so because we know how many moles must have been present in the solution before the reaction started. So now that we have how many moles of HI are present, or were present in the initial solution, let's figure out how to find the concentration of that solution. Well, concentration is always measured in capital M, which means that we have to have a number of moles divided by a certain number of liters. Well, we know how many moles were in the solution to start with, 2.93 times 10 to the negative 3 moles of HI. And if we have a volume that was present initially, then we can figure out our concentration right away. Well, perfect. In the wording of the problem, we were told that the volume of the HI solution was 25 milliliters. So we're going to take the number of moles that must have been present in the original solution, divide it by the same volume that was present for the original solution in the unit of liter. So I'm going to convert the milliliters into liters just in the denominator of my calculation. There's no reason why I can't do that. If you're not comfortable doing that, that's totally fine. You don't have to. It's just saving on a little bit of space for me. So I've converted out of milliliters and into liters in the denominator of this calculation. And I can now just crunch the numbers that are present, because the only units that are left are moles and liters, and this will give me what the concentration of the solution was initially. So 2.93 times 10 to the negative 3 moles divided by 25 milliliters converted into liters is equal to 0.117 molar. So the original solution of the unknown acid before the reaction started must have been 0.117 molar. And now that we know what the concentration of the HI was, since this dissociation of HI occurs as a 1-to-1 with the products that it creates, this concentration must also be equal to the concentration of H+ in solution, at least, again, before the reaction started. In other words, I can take this concentration that has been found, insert it for the concentration of H+, and use that to find pH. pH is equal to negative log of the concentration of H+, which is why we want to pay attention to how much H+ is present. Again, since the concentration of HI exists in a 1-to-1 with the concentration of H+, we can just take that value that we found, the 0.117 molar, insert it into this equation for the pH calculation. In doing so, we find that the pH of the original solution was 0.932. So it was very acidic indeed. This was definitely less than a value of 7. And so over the course of the titration reaction, or the titration process, via neutralization reaction, we shifted the pH to a pH of neutral, And by using the known values of our base, we're able to determine all of this stuff about our acid in the first place. All right, and with that, we come to the end of part 3's lecture. So today we have talked about what it means to have an acid and what it means to have a base. We've also talked about what it means for when they undergo a chemical reaction. We've talked about the concentration, let's say, means of measuring concentration through pH. It's more of a specialized form of concentration, but it can be thought of it that way. And we also talked about a new form of chemical analysis, meaning titration. So titrations, again, are useful in using neutralization reactions coupled with the definition of the equivalence point in order to figure out concentrations and pHs of unknown solutions. So if you would like some extra practice with this type of material, I absolutely recommend you find some, or like work through these problems, work through the homework problems, find some extra example problems, or even just reach out to me if you have a question. But until, let's say next time, if you have homework, do your homework, and class is dismissed.